Hello everyone and welcome to another session of Digital Relays. My name is Aldo and I will moderate this webinar today. The topic of today's webinar is Design for Manufacturing. Our speaker today is Aldo de Michiel.
Correct.
Hello.
Yeah, nice to meet you.
Cool to have you here. So he will host the presentation and after that he will answer your questions. The presentation will be about 30 minutes long and after that we make a short Q&A session and then Aldo will answer your question. If you're unable to answer all your questions after the presentation, Aldo will answer them via email in the next days. So last information from my side, you will all receive the link to the presentation as well as to the recording in the next days. So now I give it over to you, Aldo.
Thank you, Silas.
And I wish you an exciting webinar.
Good afternoon, everyone. My name is Aldo de Michiel and I'm a design engineer in Word Electronics Midcom. In Midcom, we design and produce custom magnetics and transformers. Today's presentation will cover one important aspect of the development process, which is design for manufacturability, or just DFM. Design for manufacturability plays a critical role in the whole life cycle of the component. It is important to consider how the part will be manufactured from the early stage of development. The later we investigate it, the more difficult and expensive becomes the design optimization. Not only cost is affected, but also overall quality and reliability are strongly linked to a good design. It is not desirable to have a power transformer with the best performances, but unreliable, unproducible, and expensive. The intention of this presentation is not to give a golden set of rules for best manufacturability, but rather raise some questions to ask ourselves when we design a transformer. Although it is good to follow some basic principle, it is better to analyze case by case and choose the optimal trade-off. So, why do we design for manufacturability? First of all, to increase reliability, because the design can be adapted to proven and repeatable processes. Secondly, to reduce cost, because we can use automated processes when possible. And this can also help us reducing the scrap. And in the end, this also helps reducing the lead time of the finished good, because we can use standard and available components. And this leads to reducing rework and iterations. Here we can see some examples of the things we want to avoid. Realizing a transformer, a functional transformer, is relatively easy because it simply requires some wire, a magnetic core, and a bobbin. But realizing a reliable transformer, this can be more complicated. For us magnetic designers, manufacturability and reliability are a priority. And in the next slides, we will go through these aspects more in the detail. As I just said, building a transformer is relatively easy, and it consists in the following elements. A bobbin, which is a plastic spool used to wind the transformer coils. It provides support, insulation, and facilitates the core assembly. Then we need the wire, which is generally made of insulated copper. The wire diameter is determined by the current. We can see a first, a second, a third layer of wire, and then the terminations. The type of insulation is defined by safety and dielectric requirements. Then we need some tape, which provides insulation between different windings. It also creates a smooth surface to improve the overall winding process. And the last layer of tape protects the winding from their environmental factors. Then, of course, we need a core, which is the magnetic circuit made of ferromagnetic materials. It improves efficiency of energy transfer between primary and secondary windings. And then we need other components, such, for example, clips, adhesive, and varnish. And generally, these components are used to provide mechanical stability of the part. Once we have chosen our core, we need to pick a bobbin on which to wind the copper wires. And broadly speaking, there are two main categories of plastics used to realize bobbins: thermoplastic and thermoset. From the pictures, you can see the results after soldering a thermoplastics, here, versus soldering a thermoset. Thermoplastics is cheaper than thermoset, but due to its lower melting point, heat damage can occur while soldering, as we can see in the picture. If the parts will go through a reflow oven, like surface-mounted parts, thermoset must be used, and this is the main reason why it's the most used plastic material for the bobbins. There are four main processes to consider during a DFM review: termination, soldering, and assembly. In most of the cases, this can be treated separately, but they can also mutually affect each other. For example, a bad winding can be the root cause of issues during soldering and assembly, as we will see in the next slide. When talking about winding, we must analyze three different topics: pinout, dragbacks, and layering. Each of them influence each other, but they can also affect the subsequent production steps, like soldering, terminating, and assembly. We will now see these three aspects in the detail. The pinout represents the way how we terminate the different windings of the bobbin pins. One important factor to consider, which is often neglected, is the internal wire routing. On the left picture, here, we can see some wire crossing nearby the terminations, and that can potentially cause mechanical stress and wire damage. On the right picture, the pinout was changed, and wire crossing is avoided, but the wire is exceeding the bobbin flanges here and here. And this can cause some issues during core assembly, potentially damaging the wire. Sometimes the best solution does not exist, and one must choose a trade-off. Now I will present a common failure caused by bad winding and poor pinout choice. We can see from the schematic here that the transformer consists in a primary, an auxiliary, and a secondary winding, and the primary winding is split in series. We will start winding the first primary section, starting from pin 1 and finishing to pin number 2. Then we will wind the second section of the primary, starting from pin number 2 and finishing to pin number 3. Now is the time to wind the auxiliary winding, starting from pin 4 to pin 5. What we can see already is that from pin 4 there is a long lead of wire that is crossing the other wires on 1, 2 and 3. And this can potentially cause some insulation damage. This can be easily avoided, and we can start winding again, but this time shifting the primary windings one pin down. Now, the first section of the primary starts on pin number 2 and finishes on pin number 3. The second section of the primary starts on pin number 3 and finishes on pin number 4. Now, the auxiliary winding starts on pin number 1 and finishes on pin 5. We can see that the lead now is avoided and the crossing also is avoided. In general, it is a common practice to wind the first windings using the internal bobbin pin first and then moving to the outer ones. Not all the issues can be detected in advance, and some problems are only visible at the sampling stage. As design engineers, we work close with our customers during all the development phase of the part, and we share eventual changes implementable to improve the reliability of the transformer. It is advisable to leave us the freedom in selecting the pinout of the transformer. In this way, we could use our knowledge and experience to choose the best pinout, optimized for mass production. We will go through another example of wire routing, which can cause insulation issues. In this case, we will wind two secondaries, A and B. A is wound from pin 13 to pin 11, and B is wound from pin 10 to 8. Finish of B is passed through this bobbin slot, and the sharp corner here can potentially damage the wire. We can see from the pictures the result. The wire insulation damage can reduce the creepage distance, potentially causing a safety fail. In the worst cases, this can lead to shortcuts between different windings or open circuits if the wire is completely cut. It is always good to build enough samples and do inspections to see if this kind of issues can be avoided. And with our DFM process, we are also minimizing the risk in mass production. In this slide, we can see how the issue was solved. Instead of passing FP through this bobbin slot, the wire was passed around the routing knob of pin 9 and 8 and then terminated. The sharp edges in this way were avoided. Now we will discuss wire dragbacks. When the number of layers is not even, for example as shown in the pictures, a dragback is required to terminate the wire at the correct bobbin site. Wire dragbacks can cause severe bumps on the build. The construction of the transformer and its performances can consequently be compromised. On the left picture, we can see a section view of the bobbin shown on the right. We can see here the volume which is occupied by the dragback. And this reduces precious volume in the bobbin, compromising the overall performances of the part. Some safety standards forbid dragbacks where wire could cross at 45 till 90 degrees. And one way to solve this is to protect the wire dragback with tape. But most of the times, this is a manual process, which we should try to avoid. The picture on the left shows a 90-degree dragback, which was manually performed. Another possibility is to spiral some turns back to reduce the crossing angle, and this can be done using the winding machine. The image in the middle shows a borderline case, where the dragback was crossing the wires at 45 degrees. On the right picture, we can see how a dragback can cause a potential core fit problem. During the core assembly, the wire here can potentially be damaged by the core. Here we can see another example of a dragback that causes a huge bump on the transformer. This not only increased production cost due to increased manual work, but also caused the wire on top to interfere with the core, risking it to be scratched during core assembly. Moreover, coupling was affected, causing an increase in leakage inductance. We should avoid dragback as much as possible. Layering is another important aspect of the DFM analysis. In the picture, we can see the same transformer, but on the right, here, two strands of smaller wire were used instead of a single bigger one. A better layering and an improved coil build is clearly visible. It is recommended to adjust the diameter of the wires and the number of strands to fill the layer completely, and possibly to wind in even layers to avoid dragbacks. Heavy wire can cause bumps that can compromise performances and the manufacturability of the part. The way we terminate the wires, it is crucial in the design of a transformer. What can we see in the picture is commonly seen on step-up transformers, where we have a heavy wire primary winding, here, on the same rail as an auxiliary winding, more on the left. Although the auxiliary winding generally does not require a large wire, it might be convenient to over-dimension it, to minimize the risk of being damaged during soldering. So let's summarize. Heavy wire can result in exceeding the bottom surface of the bobbin, and the part won't sit properly on the PCB. We should try to avoid heavy wire on surface mount parts. This can cause coplanarity and height issues. And when possible, we should split the windings in parallel and use extra terminals for high current windings. And also, as the picture proves it, we should try to avoid heavy wires and thin wires on the same bobbin side. The termination is another important topic in the DFM, because the insulation of the wire can be affected by sharp surfaces or corners, like in the picture on top right. And most of the time, this is only detectable by an expert eye during the sampling stage. When we suspect or detect a bad termination, we can use some components and techniques to make the termination safer and more reliable. And here we can go through some examples. The first solution and option we can use is the crossover tape, as it is visible here on the picture on bottom right. The crossover tape most of the time is a manual process and its placement is not consistent, but the advantage is that it uses less winding window. The second option we can use is the margin tape, visible here. It is the best cost option if winding space allows it. It is very consistent because it can be applied by machines, but it may increase leakage inductance depending on the layering. And the third option, which is not shown here but in the next slides, is tubing, which is the most effective but also the one that requires higher labor cost. It is also a good option for lead wire to prevent heat damage during soldering. I would like to make some extra consideration about tubing. Despite the extra process, it is a good solution to protect the wire damage from sharp corners and for avoiding wire crossing. On the left picture, the tubing was used to achieve a creepage distance using a non-insulated wire. The creepage distance now goes from the winding area, here, until the exposed part of the wire, which was terminated on the pin. On the other picture, tubing was used again to achieve safety distance using a non-insulated wire, but also to protect the wires from touching each other, preventing insulated damage and failures with the safety standard compliance. The non-crossing can be visible here. To give you a short break, I will now present this nice animation. Check how deep we must submerge our parts into the soldering bath. We cannot use lead to solder due to ROHS directives. Therefore, the soldering bath must be hot enough to melt the tin and the layer of insulation which is covering the wires, but without damaging the bobbin. There you go, the soldering is complete. Now the wires are well connected to the pins. But let's check this process more in the detail. As anticipated before, the termination, the type of wire used, and the amount of tin is important to achieve a good soldering and contact between pin and wires. What we see in the picture is not good, because the part should sit on the plastic standoff of the bobbin, which is visible here behind, and not on the wire termination, which are visible here on the front. We can clearly see how the wire knobs are exceeding the bobbin standoffs. It is good practice to use a proper wire for the terminals which are available, and when possible, split the wire on multiple pins to reduce the size of the wire wrap. To improve the situation shown, a thinner wire or a bobbin with more pins should have been used. What did we learn together about soldering? A large strand of wire is more difficult to solder than multiple lighter strands, because a large strand requires more heat, more time, and this can cause more insulation damage. We should avoid using heavy wire or leads wire together with fine wire windings on the same bobbin rail. Ideally, the windings on the same bobbin rail should be within 3 gauges, for example, 28 and 30 Wg. Sometimes it makes sense to use heavier wire than necessary, for example, the same wire for primary knocks, even if the current density does not require it. An advantage of this that this also can improve the bill of material, because we can use the same spool of wire for 2 different windings. And if mismatch is unavoidable, we must perform soldering in 2 different operations. For example, first soldering the heavy wire, and in the second operation, soldering the thin wires. To conclude this presentation, I will show you some videos of how transformers are built in mass production, and this is an example of a toroidal winder. We can see how the cores are added to the feeder. A mechanical arm moves the core to the winding device. Here, the core is rotated while the wire is wound using a rotating nozzle. After the winding is complete, The mechanical arm removes the toroid, which is ready for the next production step. In this machine, the human presence is only needed to feed it with cores and wires, and of course, to maintain it. In this video, we will have a look at a fully automated line. The part consists in different windings and components, and they are assembled in different steps. Between each step, there is a visual inspection and a mechanical arm moves the part through the line. It is possible to see where core mating is performed and where different tapes are applied. It is important to keep in mind that these production lines are implementable only in case of high runner parts. Due to their complexity, a minor change in the design can lead to big delays in production. The higher the level of automation, the lower is the production flexibility. While the video goes on, I would like to say that it's crucial for us, as design engineers, to know as early as possible the expected quantities per year of the part we are designing. This enables us to design a magnetic optimized for production from the outset, and by doing so, you will receive already the first samples reflecting mass production quality. I will show you another video of a fully automated line. In the detail, we can see how the machine automatically starts the winding from one pin, performs the winding, and then terminates on another pin. The second step is the auto application of the wrapper tape. Then the tape is cut, and the part is moved to a conveyor belt ready for the next step. What did we learn together about design for manufacturability applied to production? The fully automated production lines are generally preferred from us. With these ones, we can achieve the highest consistency and part reliability, because the processes are performed by machines with low human presence. In case of low volume projects, if the parts are complicated, and if special materials are used, we need to set up manual production lines, which have the lowest change time and can allow us to perform difficult operations. We have just covered some elements of the design for manufacturability. However, these are only a few points that we, as design engineers, consider when designing a transformer or a magnetics. In case you have questions or if you are interested in custom magnetics, please contact us and involve as early as possible in the design stage. Thank you for the attention.
Okay. Then I would say we can start with the first question. It's a question about the slide 6. Can you go to slide 6? The question was, you showed thermoset versus thermoplastic. How can you solder the wires to the pins without observing drop-in damage?
It is a good question. So we have to keep in mind that this material has a lower melting point compared to the thermoset. So it is crucial the time we submerge the bobbin into the soldering bath. So the first aspect we need to take into account is the time. So we need to reduce it as much as possible. And when it's not possible, we try to pre-strip the wire or to remove the insulation to make this process a bit easier. But as we see, most of the time, all the damage is, at least some damage is always present. Yeah.
Okay, thank you. Cool. Then, next question. If we send you a sample complete with spec and introductions, can this help you spending the DFM review and the sample build?
Yeah, this is another interesting question. And despite what we normally think, when we receive from the customers a sample to match or complete instruction to build a part, this most of the time does not help our DFM process and design process, because as I said in the first slides, we try to use our standard components and standard processes and techniques to design a part optimized for our production. And also in-house, we have magnetic designers with decades of experience that can design a part starting only from input and out of the transformer. And we don't require the complete bill of material or instruction how to make a part.
Okay, thank you. Then one last question I see here. Is DVM affected by the order quantity?
Absolutely. The DFM is affected by the order quantity because depending by the quantity we expect per year, we need to involve the right amount of people. We know, for example, that with low quantity, we don't need to involve all the automation aspects, but when the quantities can be higher, we need to involve the right people to give you, since the beginning, a part that will match a mass production quality.
Thank you. Then I see no more questions in the chat. Then I think we are finished with our session. If you have any questions, you can write in the chat and then Aldo will answer them via email. Then I would say thank you, Aldo, for your interesting presentation.
Thank you.
And thank you for your attention. I hope you enjoyed it and hopefully we see us on our next session of Digital Relays. And then, yeah, thank you and goodbye.